Welcome to the Power Quality Lab virtual demonstration training. This session is designed to illustrate the effectiveness of HPS power quality products in addressing power quality challenges commonly associated with variable frequency drives. Our lab is specifically designed around motor drive systems, equipped with multiple drives that manage motor generator sets, providing us with a practical and insightful demonstration environment. The demonstration will visually present the outcomes of power quality issues before and after the implementation of our solutions. Our exploration will cover an array of solutions, including line reactor, passive harmonic filter, active harmonic filter, DVDT filter, and last but not least, sine wave filter. On the input side, we focus on mitigating current harmonics that pose risks to facility equipment, neighboring facilities, and the utility grid, adhering to the IEEE 519 recommendation of 5% total harmonic distortion or less at the point of common coupling. The output side concentrates on shielding motors and drives from voltage peaks and reflected waves. The kickoff of our demonstration includes baseline measurements at the VFD input without any harmonic mitigation solution using a 100 horsepower motor drive set. This particular VFD includes a DC link choke, setting the stage for our demonstration. Initial observations show an average harmonic distortion around 30% and a power factor of approximately 0.94. This baseline serves as a reference point to illustrate the significant improvements achievable with our solutions. For Demo 2 demonstration, we will insert a line reactor into the circuit. Line reactors is typically recommended at the input of each drive, especially those without a DC link choke, to modestly reduce harmonics. A line reactor introduces impedance into the electrical circuit, helping to diminish harmonic distortion. For Demo 3, we introduce a passive harmonic filter into the circuit. Passive harmonic filter is a series-connected device consisting of inductor and capacitors configured in such a way to create a tuned circuit. This tuning process enables the filter to provide a low impedance route for specific harmonics, effectively channeling them into the filter and away from the broader power systems. It is designed with IEEE 519 compliance in mind, and passive harmonic filters are particularly well suited for configuration with a smaller number of VFDs or for loads exhibiting a stable harmonic profile. The average total harmonic distortion is reduced to less than 5%, and power factor is improved. For Demo 4, we introduce the most sophisticated solution, active harmonic filter. Active harmonic filters are best suited for environments with multiple drives or nonlinear loads, crucial and critical applications where downtime is not an option. This parallel install device employs current sensor to identify and neutralize harmful harmonics, ensuring operational continuity even if the filter is offline. It is perfectly suited for systems with fluctuating loads. The active harmonic filter will dynamically adjust in real time, effectively keeping harmonic distortion significantly under 5% and enhancing the power factor to nearly perfect levels. We're transitioning to demonstrations focused on the solutions for the load side. The VFD adjusts motor speed by altering the frequency of the power supplied. It uses pulse width modulation to create a waveform that mimics a sinusoidal shape from a direct current source. Although PWM is effective for speed control, it can generate high voltage peaks and rapid voltage changes, known as DVDT. These may compromise the motor's integrity, especially when the motor is connected by a long cable length to the VFD. Our load side demonstration begins with initial measurements at the motor input. We are using a 500 feet cable to connect the drive and motor. Observations reveal voltage peaks of approximately 1600 volts at the motor input. These peaks, reflecting back and forth along the cable, a phenomenon known as the reflected wave, can deteriorate motor insulation and damage the cables themselves. In Demo 6, we'll integrate a DVDT filter into the circuit. Positioned at the drive's output and suitable for cable lengths up to 1000 feet, the DVDT filter aims to reduce voltage peaks to below 1000 volt, and it will decrease the rate of voltage changes. Demo 7 will showcase the benefits of a sine wave filter. This filter converts the PWM output to an almost perfect sinusoidal waveform. The HPS sine wave filter, with its LC design, achieves optimal attenuation across a broad range of switching frequency, while still maintaining voltage distortion under 5%. It also strategically positions the resonance frequency peak away from operating and switching frequencies to protect the motor from potential harm. The sine wave filter is particularly recommended for scenarios with cable runs up to 15,000 feet between the VFD and motors, as well as in critical applications aimed at extending motor life and reducing downtime risks.